Hi, it's my pleasure to introduce Evan Sparks, one of the forces of nature behind MLlib and MLBase, but here to talk about model search and model optimization. Thank you.
Hi, everyone. Thank you for the introduction. My name's Evan Sparks. Yeah, I really appreciate you guys had this summit in my honor. It's really flattering. It's crazy. I've never seen so many people with my name on their badges. No, but seriously. So I am a third-year graduate student at the AMP Lab at Berkeley. When I arrived at Berkeley, just as Spark was sort of starting to take off, and it looked like a really great platform to do my research, which is into large-scale distributed machine learning. So today I want to talk to you about Ghostface, which is the code name of the system that we've been working on to do large-scale distributed model search. So just a quick overview of the badass stack, and you've seen some version of this slide, presumably. Of course, at the center, Spark came out of the AMP Lab, and in particular, a lot of the research going on at the AMP Lab today is on building sophisticated analytics frameworks on top of this wonderful engine that is Spark. So Spark Streaming, Shark, and more recently Spark SQL, as well as GraphX and MLBase are all frameworks that we're developing on top of Spark in the lab. And then, and of course, in the open source community. So most of my work, again, is focused on this MLBase component, which I'll dive into a little more detail of. So what is MLBase? MLBase is a project designed to make distributed machine learning much easier. Easier for both developers, so that is people who are developing new machine learning algorithms at scale, and also people who are trying to use these things in their business pipelines and in their processes, trying to incorporate advanced analytics where normally they might be doing some sort of simple reporting. Somebody who suddenly wants a classification model where all they used to have were sort of OLAP rollups. So the stack of MLBase looks like this. So MLlib is the first component of the stack. It ships, of course, with Spark as one of the standard libraries. It's the standard library for machine learning. MLI is a experimental API designed to simplify the implementation of new algorithms and feature extractors and the kinds of machine learning goodness you would want on top of such a system. And then the ML optimizer is a declarative layer designed to give people the ability to sort of automatically kind of come up with these pipelines without needing to be absolute experts at machine learning. So MLlib and MLI, I'll give you a kind of a status update as to where those are in just a minute. But most of this talk, I'm actually going to talk about sort of this crazy research stuff that's going on top of these lower components of the stack. So MLlib and MLI. First, MLlib we released as a component of Spark 0.8. It was just a few of us in the lab working on this initially, and came out in I guess September. And since then, there's been unbelievable open source involvement in the project. 30 contributors to MLlib and Spark 1.0. There's been continued development in the AMP Lab, but there's also been a lot of open source contributions. So things like decision trees and naive Bayes and SVD all came from open source community members. So that's been absolutely wonderful to see. MLI is this experimental API I mentioned, designed for developing machine learning algorithms. We described it in an ICDM paper last year. There's been continued development using MLI as a research platform at Berkeley. But I think more importantly, we've seen a lot of the ideas that were baked into MLI making their way into MLlib and Spark. So the model and algorithmic abstraction that many of you are probably familiar with has been in there since MLlib 0.8. In Spark 1.0, we start treating matrices as sort of a first-class citizen and start supporting both sparse and dense data, side by side with very similar interfaces. This idea of what we called ML table, but now you start to see this come into other parts of Spark. So in Spark SQL, we have schema RDDs, which are basically RDDs with schema, relational tables. Something like a data frame in Pandas or R. Is starting to come into the Spark ecosystem, and that's really great to see. And this is another example, I think, of potential for multiple parts of the ecosystem really working together. So using Spark SQL tables as inputs to ML algorithms and feature extractors, for example, is something that I think makes a lot of sense. The next piece is sort of standardizing the interfaces, both for models and for parameters and so on. That's going in MLlib 1.1. And another feature that you will probably see in MLlib 1.1 is this idea of parallel model training. And I'll actually go into a little bit more depth about that in the talk in a moment. So what does it mean to construct a machine learning pipeline? So a simple machine learning pipeline starts with like this. You've got your data in a database or a data warehouse. Maybe it's on S3 or HDFS, something like that. You then do some feature extraction. You turn your data into feature vectors somehow through some process. And then you feed those features into some model training procedure. So fit an SVM or learn a decision tree. And then finally, you end up with some notion of final model. And this is the thing the object that you can ship around and make predictions with as users click on things on your web pages or classify, hey, that's a bird in that image. And so this is the thing that you can use to sort of, make predictions. So in reality, though, constructing these pipelines is sort of a highly iterative procedure. So you have this, you'll evaluate your model, and suddenly, the error will be junk. And you'll realize you need to go back and add some new data. Maybe you need to try a different feature extraction procedure, or maybe you need to experiment with different kinds of model families. So maybe it's fitting an SVM instead of logistic regression or something like that. Fiddle with the hyperparameters that make the model work or not. So like I said, this is an iterative procedure, and our grand vision is to sort of automate the construction of these pipelines. So this trying a bunch of different knobs to turn and so on is a very manual process and something that we think that the computer can automate pretty well. So, but that's kind of an impractical thing to do all in one shot. So we're starting with one aspect of this iterative procedure, this building these pipelines, and that is model training. So this is what we mean when we're talking about automated model selection or automated model search. So what are the different model families I should be trading off between, and what are the different knobs of those families I should be fiddling with? So just to give everybody a refresher on what I mean when I say training a model, fitting a model. Well, what I mean is estimating some statistical parameters that are useful for making predictions. So in practice, what this looks like is over my data set, I might compute some kind of delta to my model, my current model, and update it. So this is things like gradient methods and stochastic gradient descent. You also see a very similar kind of procedure when you're doing things like decision trees. So you compute some delta to the histograms and you update them. But this is sort of an access pattern. This is a bunch of sequential scans over the data in practice in order to fit a model that works pretty well. And so the math might be different between each of these model families, but that access pattern is something that we see over and over again. So in practice, what this means with Spark is, on a reasonably sized cluster, we can, take a few, tens of passes over our data and fit an SVM on 200 gigs of data on a 16-node cluster in maybe a couple of minutes. So that's kind of the number I would keep in mind, reasonably big data set, a couple minutes to fit a model. So the tricky part is that, as I mentioned, if we had only one, statistical procedure that we used to build models, maybe it was just, if we only knew about logistic regression, our task would almost be done. But in fact, we have a bunch of different reasonable classification models that we can use. So logistic regression, SVM, tree-based, there's a whole slew of acronyms that I could throw at you, and I won't. And then each of these algorithms also has a set of hyperparameters to tune. So these are those little knobs that make your model fitting just right or totally wrong. And actually setting these in practice is often fairly experimental. The other portion is this feature extraction and featureization. And again, that's not what the focus is today, but it's important as another dimension to keep in mind when you're building these pipelines. So maybe I should try different text features if I'm fitting a text processing pipeline. So n-grams, how big is the n? Or TF-IDF, how many terms do I go out when I'm fitting my text model? Similarly, for images, there are similar trade-offs to make. And then there are these sort of domain-independent trade-offs that you can make as well. So again, with model search, we're really focusing just on algorithms and hyperparameters for now. So how do you actually do this? So it turns out in practice, people are doing this all the time. And one approach is to sort of try it all. So I have on the right side of the slide here, two hyperparameters I might want to tune. Say learning rate and regularization for something like logistic regression, so L2 or something like that. And each of the points on this space represents a potential setting for the hyperparameters of this model. Maybe the best answer is learning rate somewhere and regularization somewhere in that lower right corner there. Now, in order to find that, I might actually have to try and fit several models. So I might try and fit a model in this corner and that point and that point and so on. And this is an approach called grid search. You can kind of imagine the nested for loops in your head sweeping over the space. And so eventually, I fill up the space and I get to a best answer, which is maybe, I try to point close enough to that best answer and I think that's pretty good, and I'm done. And so this is with 2 dimensions. You see how many red dots there are on my screen. You can imagine as you add dimensions to this hyperparameter space, that space starts growing exponentially and that volume gets really big really fast. And so, given that these models are expensive to train, perhaps there's a better way that we can train models in reality. So I'm going to propose a better approach, which is the one we study, which takes advantage of 3 basic optimizations. So first is better resource utilization through batching. So instead of training 1 model at once, I might train 4 or 10 models at a time. And you're going to see why we can do this almost for free. I'm going to talk about some algorithmic speedups. So instead of training every single model to completion, we take advantage of the fact that we know that model training is an iterative process and we can maybe stop some models early. So maybe some models don't get trained to completion and we can train more in the same amount of time. And I'm going to talk about sort of better search strategies. So instead of walking over this entire grid, maybe I can do something to get me to that best answer more quickly than the sweep. So for the remainder of this talk, I'm going to talk primarily about these 3 optimizations. So first is this idea of better resource utilization through batching. So the key idea here is that, at least in today's computers, processors are significantly faster than memory. And what I mean by that is that we can saturate the memory bus with something like 5 gigs a second per core. So that gives us, if we're streaming data into our processors through memory, we can read something like 500 million numbers per second. Meanwhile, we can probably do something like 15 billion flops per second per core. So that leads to this impedance mismatch where we have, for every number we read from memory, we could do maybe 25 numerical operations on it in the same time. So what does that mean for modeling? Well, a typical model update, one of these deltas I talked about earlier, basically requires something on the order of 2 to 4 flops per double. And this is going to vary depending on how complicated your model is, but for sort of the bread and butter ones, this is about what we see. So what that means is this, with this 25x impedance mismatch, we can do something like 7 to 10 model updates in the same amount of time that we could do by using otherwise idle cycles. And so this is pretty cool. It means that we can actually train maybe 7 to 10 models in parallel, while in the same amount of time we train 1. Again, assuming that models are kind of small and fit in cache and we're not shuffling them back and forth in and out of main memory. And so what do we see when we actually implement this in MLI? Well, if we do it in sort of the naive way, we see something between a 2 and 5x increase in models trained per second. So that is, for every data point we read in, we just update, say anywhere from 1 to 10 models in parallel. And so 2 to 5x doesn't quite get us to the 7 to 10x that we would have hoped to see theoretically. And a lot of this comes from, the sort of typical JVM stuff, the unboxing, there's of course some network overhead and so on in there. But we basically see something like a 2 to 5x speed up for again, models that are sufficiently kind of small. It turns out that you can do this in a sort of more clever way with batch matrix updates. So we instead of doing our model updates as a series of basically dot products between vector dot products, we can turn this into matrix multiply. And leverage all the crazy hard work that has gone into BLAS over the last 30 years and get cache-aligned, nice, really fast, sort of dense multiplies that go faster than sort of the n-cube that you and I would code up natively. And so what we see when we turn on this matrix multiply operation, and you can kind of ignore the numbers at the top here because they were run on sort of on a slightly different cluster, but the speed ups at the bottom are what's important to focus on. So as we turn up this batching parameter, this batch size closer to 10, we really do see 7x speed up, again for sufficiently small models, but it works even better on larger models. Than the previous version. So there's still some stuff to do here. These are very early results. But the idea here is that if we can potentially train models in parallel. And in practice, this might be an important thing to do for a data science workflow. So the second optimization I want to talk about is algorithmic speed up. So how can we make this model search go faster? And so this is going to be, again, taking it into account this idea that each of the points in our hyperparameter space represents training a full model to completion. But it turns out that the models are trained by some iterative process. So what I've got on the right here is a graph that shows kind of error convergence for two different models. And you can see there's a model in blue, model B, that's not converging as quickly as model A. And if I gave each of these models some budget of, say, 10 passes or 100 passes through my data, I could say, just looking at it myself with some confidence, I don't think model B is ever going to get to the same answer as model A. So maybe we can just stop this thing early and kill it off when we realize that it's probably never going to converge. Now, the machine learning people in the room are probably cringing, because how can I prove that this model is never going to get better than that model? And the answer is we can't, or at least we haven't yet. We are working on looking at this in sort of a more principled framework with multi-armed bandits. But the answer is that when we do it in practice, we actually get a significant savings in terms of like total passes over the data, total epochs, something like an 85% savings. And we converge to almost exactly the same answer. So we tried this on 5 different data sets with this early stopping heuristic turned off and then turned on. And we see that roughly 85% savings in terms of total passes over the data. And then what's the more important thing is that we get to almost the same answer as we would have if we had trained every model to completion. So we compare against a baseline on the right side, and then the optimization turned off and then on the bottom here. So the answer is basically the same, despite maybe saving a bunch of potentially necessary work, I guess. So the other thing, there are lots of other things we can do to sort of accelerate convergence. So using fancier methods like accelerated gradient methods, AdaGrad or LBFGS, could speed up convergence quite a bit. These are things that LBFGS is now in MLlib, and we should just turn this thing on. So finally, the last bit of optimization I want to talk about here is improved search. So the question is sort of what search method should we use to go over this hyperparameter space? So it turns out that there are a lot of existing search methods for these what we're calling derivative-free optimization problems. And that's not our word. That's something that's existed in the literature for years. But you can think of grid search and random search as versions of derivative-free optimization techniques. Basically, you're trying to find a minimum over some function that you don't know anything about the curvature of or whatever. I don't know what the derivative between decision tree and SVM is, for example. So all I can do is sample the function. I can get grid points, and now I want to converge to a global minimum very quickly. So grid search and random search, as I mentioned, are methods for this. Nelder-Mead and Powell's methods are things that have been around since the 60s. Simulated annealing is another one that falls into this family. And more recently, there's been some interest from the Bayesian community in this exact problem. And so 3 methods that are recent at NIPS, Spearmint, SMAC, and TPE, are things that we tried. And what we wanted to do here was compare, in this case, 7 different search methods across 5 different data sets. And I apologize, the chart is kind of confusing, but what we want to see is bars that are red. So on the left side, we have the fewer number of function calls in red, higher number of function calls, 15 up to, say, 600 in purple. And what we want to see are bars that get low very quickly. So what we see, interestingly, is that random search actually outperforms any of the sort of classical methods, which is surprising. How can random be that good? But a couple of the Bayesian methods anyway actually do slightly outperform random methods, so we went ahead and implemented them in our system. So putting it all together, we have the first version of the MLBase optimizer, and we wanted to, say, take a data set that was, say, 30 gigs of image features, run it on a 16-node cluster for a while, and compare do an ablation study of what turning these various methods for optimization on and off do. So basically, if you do the naive thing, grid search with none of these optimizations, you take something like 800 to 1,000 minutes to fit 128 models. Now, when you turn on both batching and this early stopping and use, say, TPE or the random search, you finish much faster. So something close to 100 minutes. And more importantly, I think, you converge to a pretty good answer very quickly by using one of these more sophisticated search strategies. So you get to a good answer within an hour, I guess, in these experiments. as opposed to potentially taking days of computation time, which is the difference between your lunch break and a weekend job running in a practical setting. So that's pretty exciting. So then the question is, of course, does it scale? Model search at scale, I guess, is the title of the talk. So the answer, yes, it scales. We run on a 1.5 terabyte data set on 128 nodes. This is thousands of passes over the data doing the search procedure, and we can get to a good answer within 11 hours, again, versus like what would be a week of time if we just did the naive thing. So that's kind of exciting. Okay, so I've given you an overview of kind of the work we've done on the model search pipelines. I think I have at least a few more minutes. So I want to talk a little bit about real-world pipelines. So this is sort of the future direction for our research. So earlier in the talk, I gave you this picture of a simple machine learning pipeline. So data to feature extraction to model training to final model. And that's kind of nice, and we focused just on what we could do if we really, we had all the degrees of freedom we wanted on this model training thing, and we could really search through it. So what does a real machine learning pipeline look like? Well, here's one that we coded up that looks a lot like, that's a sample image classification pipeline based on some work from Adam Coates and Andrew Ng back in 2012. And you can see that this starts to look a lot more complicated than that little 4 boxes that I showed you. In particular, we have this test area down on the bottom. We have a series of steps going on at the top. We have a second machine learning method, k-means, as part of the feature extraction pipeline. And then there's also this linear solver thing on the right side. And so it turns out that each of these boxes may or may not have its own hyperparameters to tune. So suddenly that search space of how do I find the model that actually works as a classification model given my data gets big very quickly. So things like how big is the convolution window, how big are my pools, what different polynomials do I apply to my data after I do the pooling step, again, which linear solver do I choose given my data. These are all things that the user would have to decide and that we hope to automate shortly. So that's the idea. We're working on a DSL in Spark, in Scala, to describe these pipelines. We have a few built. You can hope to see a release of this stuff from the AMP lab by the end of the summer. So in future work, we're working on thinking about choosing between model families, so maybe looking at multi-arm bandits as a way of doing this. We're training lots of models together at the same time, so maybe there are some ensembling methods that we can use. So we're training all these models. We might as well use them and kind of use the insight they give us for free. We may want to leverage sampling, so it may not make sense to fit to your entire data set always. In practice, I've seen people take a subsample of their data, fit a model that kind of works, and then scale it up and apply it to the full, say 200 gig data set. Faster learning methods, again, incorporating these things like AdaGrad or LBFGS into the pipeline. Better parallelism for smaller data sets. So this is the idea that not all data is big data, but we can still leverage cluster resources in order to maybe train models faster. So maybe I broadcast my data out to all the nodes in my cluster, excuse me, all the nodes in my cluster, and train sort of local models there, and then come back and decide on what gives me the best result. Incorporating feature extraction into this pipeline, as I mentioned, is huge and is sort of the current focus of our work. And then finally, people say you're searching this huge space, you're trying all these different things. How do you know you're not just boiling the ocean and getting lucky and finding the model that kind of works? So this is something that statisticians have been working on for years with multiple hypothesis testing. So incorporating that idea into our work, I think, makes all the sense in the world. So that's it. I'm happy to take questions on anything, and please feel free. Yeah?
Do you compress matrices? Do you decompress them for caching of the CPU?
So do we compress matrices? That's going to depend on which size and shape you're talking about. So when we're doing our dense work, generally we're not compressing our matrices, at least not when we're doing the operations on them. With sparse matrices, we do CSR type encoding to get tighter stuff. Zhangri gave a talk yesterday about the sparse matrix support in MLlib, so I encourage you to check out that video if you haven't seen it.
Do you vectorize the operations?
So we vectorize the operations. We don't vectorize the communications. I mean, we vectorize the communications to the extent that we don't send a byte at a time. We send, full objects. Does that answer your question?
But you can like do vector operations like on flows.
Yeah. So we take advantage of the built-in BLAST libraries to do vectorized operations whenever possible. Yep.
So I think most of the methods that we are talking about is classified static. So if you consider methods like which consider a particular classifier, for instance, like you could have used like the entire path solution for some of the classifiers, and that would give you the entire path based on some initial declaration.
Yeah. For example, you can for some of these methods you can kind of get the regularization or the optimal regularization parameter for free. Rich regression is a good example of that. So we haven't incorporated that into this work, but that's a very natural thing to do. Absolutely. Yep.
Can you comment on how much customization can be done to the model selection criteria at this point?
What do you mean by customization? Which?
You're using n-fold cross-validations, can we tune the sizes, all that kind of stuff?
Yeah, absolutely. So at the moment, the code is basically set up so that you can define a hyperparameter space as sort of an abstract thing. A set of hyperparameters and maybe nested. You can pick the search method that you want to use. The code is fairly simple, so if you wanted to try a slightly different search method, maybe vary the number of folds for a k-fold cross-validation, that would be fairly simple to do. Yep.
Do you have any insights on why certain search methods, particularly among the base maps we looked at, were performing better than others?
Yeah, so it was a little surprising that this spearmint method didn't work for us. We're in conversation with the authors on that one to figure out what the discrepancy there is. Between the SMAC and the TPE, which are the two search methods that seem to work really well in our hands, TPE is sort of simpler. It basically starts with a random search and then hones in on the area that seems to be giving it the most juice via basically setting up two distributions and sampling from the one that seems to have better performance. SMAC does a random forest-based approach, which my intuition is that would work better as you start to collect lots more data points. You just get sort of a more fine-grained view of the search space. But we're really operating in the regime where you've got low tens to maybe 100 data points to choose from. Yep, back there. Oh, sorry.
Optimizing using the CPU cycles while the CPU is otherwise waiting for memory.
Mhm.
Does that affect the portability of your approach?
I don't think it really affects the portability. I mean, I think it's gonna, there's this concept called machine balance, which is basically the speed at which memory streams through versus the flops per core. And so that is something that has, you look at the numbers over the years, and it's been sitting around 25 for most modern CPUs. That said, if some new memory bus architecture comes out, or some Intel releases some new CPUs, that could change this balance number. But the trend has been actually towards more CPU per amount of memory transferred over the last few years. Yep, question.
So is there a possibility of contributing to the project? Is it already an open source project that is open for the public, or is it closed?
Yeah, so I fully encourage you to contribute to MLlib. That's sort of the main area of open source contribution right now with machine learning on Spark. That said, this particular model search project, we're hoping to have a public release out sort of near the end of the summer. It's going to depend on how some of our paper submissions go and that sort of thing.
So right now it's not available to the public?
No, not yet. Those upper level components. Yep. One more? Yeah.
Do you have any problems like machine models that fit well in the cache like that?
Yeah, I mean, so in this case, we've kind of tied our hands a little bit and said that we're going to take the features that the user gives us as input, and we're not going to yet focus on like how do we select those features or how do we enumerate new ones. And so the model size is almost always determined automatically by the size, the number of features that the user gives us. So if you're dealing with a really, really wide data set, for example, say hundreds of thousands of features, you might not be able to get some of the full benefits of some of the optimizations I talked about. But that's going to depend on your data. All right, great. I think being held off stage, thanks again.